Good afternoon, everyone. I am Min Sang-mi, today's lecturer. In today, I
You
will.
should speak louder for online.
Okay. Good afternoon, everyone. I am Min Sang-mi, today's lecturer. Today's lecture, I will give a simple explanation about the line drawing problem. Before start my main lectures, I will briefly explain about the basic proportions. The first one is length depth ratio L over D. It is related with structural design. The second one is length beam ratio. It means lineage and it is related with maneuverability. The third one is length depth ratio L over T. It is related with both slamming damage during several weather in Korean. The final term is beam depth ratio B over T, and it is related with transverse stability and wave making characteristics. From now on, I will start my lecture, and my lecture is composed of big two parts. The first one is general approach, and second one is techniques. First, general approach. As you well know, and for this based on as you well know, and as you can know, see these figures. The shape of the ship is three-dimensional, not two-dimensional, and also it has curved space. However, the papers and line drawings are clearly 2D dimensional and with the line and 2D papers. So it is key problem that describing three-dimensional shape into the two-dimensional shape using line drawings. Two-dimensional lines can be obtained by curving the shape based on the virtual plane, and each cross sections we get the lines above the shape. And after by superimposing the many contours at the same time, we can reconstruct the 3D shape of the ship into the two-dimensional papers. A summary of this slide is given. A problem of drawing a curved three-dimensional surface on a flat sheet of paper. The second, a series of two-dimensional contours from parallel cross cuts and image based on imaginary virtual sections. The second, a cartograph contours maps with constant calibration. Or maybe if you think of slicing or local bread, maybe it will be easy to understand. Next, I will briefly explain the concept of the modulo. If we get the 2D line drawings based on the methodology that I explained earlier, the size of the line drawing is not actual size but reduced size. So it is necessary to change the reduced scale to the actual size. Therefore, also the place is needed. Therefore, a place where the drawing of a reduced scale ship is transferred to the actual size or a work of making a model is called the modulo in Korean. Maybe this slide is a key slide of my lectures. This is my lectures that explain the basic principles of getting 2D contours based on the 3D object. For each understanding, I take a mountain as an example. For 3D shape of the mountains, we can imagine the virtual sections that at different elevations, and each elevations we can get the contours. Also, if only one contour is given, we cannot construct the 3D shape into a 2D plane. However, if you have the sufficiently many cross sections, imaginary virtual plane, and therefore we can get the many contours, and if we plot the many contours at the same time or superimpose, we can construct 3D shape of the something object into the 2D based on the 2D contours in the paper and line drawings. And earlier, I explained as a mountain just as an example. However, our ultimate objective is construct the line drawings based on the 3D shape of the ship. In Cartesian coordinate, we can consider x, y, and z axis And based on the three different axes, we can consider three other planes: xy plane, yz plane, and gx plane. Based on each plane, we can imagine cut the shape along the certain axis. For example, we can cut the shape based along to the x-axis, the direction of the shape. We can get the red contours, and the superimposed red contours is the body plane. Based on the shape, in similar way, if we cut the shape along the z-axis, we can get the blue contours, and superimposed the blue contour is hypergrid plane. It will be explained more detailed later. Finally, if we cut the shape into the line of y directions, we can get the many yellow contours, and the superimposed of the yellow contour is shear plane. It will be explained later. The first thing I want to explain is the body plane in Korea, Jeongmyeon-do. Let's imagine the cut the shape along the length of the direction and imagine consider the y plane. For certain cross section, we get the contours, and if we have sufficiently many cross sections, we can get multiple contours. Finally, drawing a multiple contours in only one paper, we can construct body plane. In general, the shape of the hull is usually symmetrical, so the naval architecture composed of body plane at big two parts. The right part of the body plane is composed of whole body line of the ship, and the left part of the body plane is composed of left body line of the ship. This picture is the real example is that a body plane composed of the real 3D-dimensional ship. So I earlier, the body plane I explained earlier, and with additional two lines. The one is outline representing the shape of the boat in Korean Sunsu, and the second line is outline representing the shape of the sun in Korean Sunmi. If you have information about body plane or outline about boat, outline about sun, you can completely definition the whole form. However, also it is sufficient in calculating the recovery stability or resistance performance of the ship. However, in general, naval architecture uses two other families of contours, and next slide will give an explanation of these other two families of contours. The first one is water plane lines. Let's consider GX plane of the impartation coordinate and virtual plane parallel to the base plane of the ship. Okay, by applying same principles, we can get multiple contours, and if we superimpose the multiple contours in one drawing, we can define water plane lines of blue contours in the schematic. And due to the symmetry of the shape of the ship, in general, naval architecture show only half of the water plane lines. Due to these reasons, another name of water half line is half grid plane also, and this picture is an example of water plane lines for some three-dimensional ship. The second line is the bottom lines in yellow contours in the schematic. Let's consider XY plane at the top ship along the XY plane. Let's imagine virtual plane parallel to the center of the hull, and by applying same principles, we can get many multiple contours and multiple lines, and superimpose multiple contours in one drawing. We can construct bottom lines of the ship. And this picture is an example of bottom lines that compose based on the three-dimensional ship. Or maybe this slide is summary of today's lectures. As you well know, the shape of the shape is three-dimensional, not two-dimensional. So it is very hard to. It looks like not easy to describe the 3D curved space into the 2D line. However, if we consider the three-dimensional Cartesian coordinate and consider x, y, z axis and three different planes, we can construct many contours for each cross section. The red cross, superimposed of red contours is the body plane. The contours by cutting the shape along the length of the ship direction. It is the first line drawing. The second one is blue contours. That what the name of blue contour is water plane lines. That contours based on the virtual plane parallel to the base plane. The final term is the bottom lines. Hello contours in the schematics. The contours based on the virtual plane parallel to the center of the curve. By dividing the shape into the three planes and based on the each planes at the each lines, we can reconstruct a three-dimensional shape into the two-dimensional lines. It is the basic principle of the line drawing of the shape. Okay, let's show simple video, please.
To demonstrate what service we can offer for design hull shape. Import initial information. In general, to define initial hull shape, we can use any available information. It can be general arrangement plans and profile, 2D preliminary lines drawing, (3D lines drawing), different type of CAD files with hull surface. We can use even paper drawings if necessary. Based on initial information, hull surface can be created quickly, and with high quality. Decks, appended parts, and all necessary surfaces can be also created. Initial stability data, such as displacement and center of buoyancy, can be controlled. Hull shape optimization. Modern methods of computer fluids dynamic lets us to make ship resistance predictions. Results of the CFD calculations can be visualized together with hull lines. Waves pattern, pressure distribution around hull, streamlines show us area of the hull surface we can improve. After several CFD runs, hydrodynamic quality will be optimized. Hull shape output files and documentation. Output documentation can be presented in several different documents. It can be classic.
It is the slide of my lecture. I will briefly explain the principles that construct 3D-dimensional of the shape into the two-dimensional lines. And at this time, the design it is equal to line drawing should be paired. And at this time, repair means the line drawing should be expressed as a smooth surface without the changing curvature. Let's think about only one directions and drawing only one smooth, only one curve. It is not a challenging problem that drawing only one curve in a smooth curve. It is easy problem. However, as I explained earlier, the shape of the shape is three-dimensional, so we need at least three directions and three different curves. Therefore, draw all three curves as smoothly is a challenging problem, so it's very hard. Due to this, the general approach is to draw the first version of the line drawing and modify, and until the perfect smoothly curve is obtained. The detailed process will be not considered in my lecture, or maybe Professor Khan will explain in the next class. However, the short thing is that nowadays, thanks to the development of computers and mathematical techniques, it is more easy to adjust the curve of the line. So in nowadays, due to the development of the technology, naval architectures can more easily adjust the line drawing curvature process. This is my latest slide of the lecture, and thank you for listening.